I want to talk to you about the bonding in octatetraene. First, notice that octa means 8, tetra means 4, and this ene means double bonds. And so this means I have 8 carbons with 4 double bonds. And usually they'll number them. So if I number this 1, 2, 3, 4, 5, 6, 7, 8, I can actually say that these double bonds start at 1, 3, 5, and 7, meaning every other carbon-carbon bond is a double bond. Now, the electrons in these double bonds are what we call pi bonds. The ones in between are called sigma bonds. And these pi bonds actually have some special properties. I want to remind us that we have 2 electrons in each bond. And so I must have, with 4 double bonds, I must have 8 pi electrons. And so 8 divided by 2 makes 4. I have 4 double bonds. Good, I'm good to go. So I actually want to talk about the molecular orbitals for these pi electrons. And if I have 8 pi electrons, I need to construct an energy ladder that has a total of, it turns out, 8 orbitals. 1, 2, 3, 4, 5, 6, 7, 8. Good. I'm going to just number these to remind myself what the heck is going on. And so I have 8 pi molecular orbitals. The lowest in energy I've labeled 1. And now I have to fit 8 electrons into these 8 orbitals. And if you remember, for every bond that gets formed, we pair up 2 electrons. So let me put my 8 pi electrons in. And so this looks like 4 bonding orbitals. And this one, number 4, is called the highest occupied molecular orbital, which I'm going to abbreviate MO. And sometimes we refer to this as a HOMO, which stands for highest occupied molecular orbital. And then this number 5 is the lowest unoccupied MO, or a LUMO. So if I put some energy in here and take one of these 2 electrons and promote it up to the next level, the energy that's required depends explicitly on the energy difference between levels 4 and 5. And so we refer to that as the HOMO-LUMO energy difference. And then this gives us some idea about the wavelength of light that is required to take one of these electrons and promote it from the HOMO up into the LUMO.